Chapter 1 is about the structure of metals. And probably you have seen these topics in materials engineering class or mechanics of solids. But it is important to understand the structure of metals because it will directly affect manufacturing properties, how manufacturing parameters are affected by the structure of the metals, or how structure of the metals are basically affected by the manufacturing parameters. So therefore it is important that we review these topics. So we're going to review the crystal structure and arrangement of atoms and how they determine basically the material behavior, and imperfections such as dislocations, which is a very important topic to understand because it is directly related to the plastic deformation, meaning the permanent deformation, which is key in manufacturing, right? And then we're going to learn about grains and grain boundaries and how basically these characteristics of the materials affect the properties and manufacturing parameters. So we can understand also why certain defects can form during the manufacturing processes and how we can prevent them. Okay, so let's start. So what is manufacturing? It is the process of converting raw materials into products. It encompasses the design and manufacturing of goods using various production techniques. So when we say manufacturing, it includes the raw materials and it includes the design part and of course the manufacturing. Okay, so the products, they can have only a single component, like a paper clip or a spoon, right? But many products we see, they are made from a variety of materials, as you can see in this figure for a car. They are made from variety of materials and then they are assembled together basically, and using a variety of different materials. And in this figure you can see that, for example, let's look at some parts that are making up the car. And as you can see that, for example, the engine block here is made up of cast iron or aluminum. The body of the car, for example, is made from steel, aluminum, or a composite. So you see different parts of the car is made up of different materials, okay, that are assembled together to make up the overall product. Okay, so when we say engineering materials, what are they? What are the families that is included in the title engineering materials? And why it is important to understand that, right? So when I say aluminum, for example, you guys need to understand that's a metal, right? And if I say, for example, epoxy, you need to understand it's a thermoset plastic. And I say aluminum oxide, you guys immediately should understand that's a ceramic. This is important because these material family groups, they all have common properties. And if you understand, let's say this is a plastic or this is a metal, then you're going to understand how to approach to manufacture them, how to process them. Okay, so you need to be familiar with the name of the materials and which family of materials they belong to. So when we say metals, can be ferrous, non-ferrous in general, and ferrous are the metals that has common common material in it is iron, like steel, stainless steels, etc. And non-ferrous ones that doesn't have the iron element, it is like aluminum, copper, titanium. When we have plastics are separated to three groups, and here thermoplastics, thermosets, elastomers, all showing different characteristics, and all are manufactured in different ways, right? With different parameters, different processing technique. So a manufacturing technique that is capable of manufacturing metals might not be able to manufacture plastics. Therefore, it is important we understand which materials are belong to which families. So elastomers, for example, rubbers, right? And those are elastomers. And ceramics are compounds. Compounds means two elements coming together and forming a compound. But these two elements have to come together at a certain ratio. For example, aluminum oxide, right? Aluminum oxide, 2 aluminum and 3 oxygen coming together, or silicon carbide, right? 1 silicon, 1 carbon coming together. It's a compound. So that's being said, oxides, nitrides, carbides, glasses, graphite, diamond, they are all included in the family of ceramics. Okay. So it is important, you guys, if I tell you what is a silicon nitride, then you need to understand that it is actually a ceramic. Okay. So the composites are basically 2 or more materials coming together, and we're gonna see more detail, right? So you can put together plastics together with metals, ceramics, basically to achieve certain desired properties. So when we look at the behavior and manufacturing properties of materials, when we say the structure of materials, we are talking about like atomic scale, right? The atomic bonds, the crystalline structure or amorphous structure, polymer chains. They are together forming the structure of the materials. And mechanical properties, you guys are familiar with the strength, ductility, elasticity, hardness, fatigue, creep, toughness, fracture. We all gonna see those in the next chapter. And then we will see physical and chemical properties that are important during the manufacturing, like density, melting point, specific heat, conductivity, electrical, thermal expansion, magnetic properties, oxidation, corrosion. Okay. So what about the property modification that is used during manufacturing? Like we can apply heat treatment, hardening or strengthening, annealing, tempering, surface treatment, alloying, and etc. Right? Reinforcement, composites. All we're gonna see and cover in the following chapters. Understanding the structure of metals allows prediction and evaluation of their properties, such as strength and stiffness, whereby appropriate selection for specific applications can then be made, right? For example, we see here turbine blades that are manufactured with 3 different techniques. And all of these techniques, of course, resulted in a different structure and therefore different properties of the same product is obtained actually. So in the first A, we see it is made with the just conventional casting, and B is directional solidification. Okay. So in a certain direction, the atoms are aligned, basically, the grains. And then C is a single crystal. Okay, so all atoms are aligned at a certain direction. Okay, so therefore the single crystal turbine blades, although they are expensive, they are showing much better properties compared to other blades like A and B. And you can also macroscopically observe how homogeneous the structure looks, right? So if you look at an outline of topics described in this chapter, so when we have a liquid metal, this is usually how we start in manufacturing. We first solidify it, right? And when it solidifies, it's forming the unit cell. And the unit cell is what we learned as BCC, FCC, HCP structures. And determination of properties starts from the formation of unit cells. Okay, so BCC or metals will behave differently than FCC. This is how important the atomic structure, atomic configuration is. Then those unit cells will come together and form the crystals. And inside the crystals, we will have imperfections, dislocations, and they will be responsible for the deformation, how much strength it requires during manufacturing, for example, to shape the part. And it is directly related to the dislocations inside the material, okay? So, of course, crystals can be single crystals, just like we have seen. Those are, the example was turbine blades, for example, and polycrystals, okay, paper clips, bolt springs. And of course, when we are defining polycrystals, we need to include the information of grain boundaries and isotropy, etc. Just want you to visualize what a single crystal is. So let's assume you are looking under the microscope and seeing the atomic arrangement, right? So this is our view here, we see. And then when we are talking about single crystals, all atoms inside the single crystals, they are aligned in the same way, in the same direction, okay, as you can see, same direction, all of them, okay. So there is no difference in the alignment direction of atoms within that material. But when we are talking about polycrystals, there are atoms that are at certain regions, and those certain regions, the atoms are aligned in different directions. Let's say in this region they aligned like this, okay, in this direction, okay, and here they this region they aligned like this. They come together in this direction, okay, and here like a 45 degree, let's say, okay. My beautiful sketching technique. Okay, so you see these atoms will at different regions will align in a different direction, and they form the grains. So this region will be a grain, and it will be separated with a grain boundary, right, from the other region where the atoms are aligned in a different order, okay. So all of them, we have now 3 grains, and all the atoms in these grains are aligned in different directions. So this is then many, meaning polycrystal, right? And then this is a single crystal. Of course, it is important to understand this, because this type of alignment of atoms directly affect the properties, and of course it affects the processing techniques, how do we manufacture them, and it affects the formation of defects and all kinds of other manufacturing properties that we will see in our further topics. Okay, so let's start with the type of atomic bonds. This is so important because the type of atomic bonds will directly, indirectly determine many of the properties. For example, elasticity, okay, thermal expansion coefficient. Okay, so some properties of materials are directly related with atomic bonds. So we are all familiar with this, right? Ionic bond, covalent bond, metallic bonds. So when we say ionic bonds, those are when one or more electrons from an outer orbit are transferred from one material to another. A strong attractive force develops between these two ions, like sodium and chlorine. Okay, so there is an electrostatic attraction because sodium is plus, chlorine is negative, right? And then there's, because one electron is given and another received, therefore what is happening, they are forming an ions, and these ions are attracted to each other. Okay, and so many of the ceramic materials, so ceramic materials are mainly made up of ionic bonds. Okay, so therefore many of the characteristics of ceramic materials directly related to, such as low thermal electrical conductivity of ceramics, right, or low ductility, these are all directly related to the ionic nature of the bonds of ceramic materials. So that is how important to understand these. And covalent bonds are the bonds that we observe in polymers. Okay, because polymers, they are made up of large molecules. The main element in polymers is carbon, and carbon-carbon bond. These are covalent bonds, and they are very strong. And I'll give you some question to think about for now. So first, covalent bond is happening because the outer orbits are sharing the electrons, right? So that is how the covalent bond is happening. So, and the carbon-carbon bond is a covalent bond, and that's the main bonding in polymers, and it is a very strong bond. So we know that now the polymers have a strong bonding, carbon-carbon bonding, but we also know that polymers are not strong materials. They are easily deformed. They don't require a lot of strength to deform. I mean, think about the rubber, right? Rubber band. You can easily deform it. So even though it has the strongest bond, the covalent bonds inside, why it is we can able to easily deform these materials? Why doesn't it require a lot of strength to deform these materials? Just think about this. Okay? And if you cannot figure it out, just let me know. So metallic bonds, as the name implies, observed in metals. So besides metallic bonds, metals can also have covalent bonds inside. So metallic bonds is basically explaining all properties of metals, because basically metals have free electrons inside the structure. Okay, so these free electrons shared between all the atoms inside, and these electrons can easily move inside the material giving the metals a very high thermal and electrical conductivity. So as you can see, many properties we observe in materials can easily be explained by the type of the bonding that material has. Okay. So now we learned about atoms and the bonding between the atoms, and then 3D arrangement of these atoms in space, right? They can only be arranged in a certain configurations. Okay. And you guys learned these in materials engineering class. And when they are arranged in an order, these atoms, we call it crystals, okay, or the crystal structure or crystalline structure. So these are the smallest repeating units in the structure. The smallest repeating unit is what we call the unit cell, right? Smallest group of the atoms exhibiting the characteristics of the lattice structure or the crystal structure of a particular metal is known as the unit cell. So you see this is the unit cell of what we call the body-centered cubic, the BCC structure. And this is repeating, right? Repeating in 3D and forming the overall the crystal structure, okay, or the material itself. And why it is important? And this type of course, configuration of atoms directly related to the atomic bonding. Certain type of bonding will result in BCC, or certain type of bonding will result in FCC. Usually, covalent bonding is resulting in a BCC structure, for example. So it also comes from the atomic bonding. But certain materials will have a BCC structure, certain materials will have other types of structures we're gonna see. But right now for body-centered cubic, you guys remember this. That's the unit cell here. The corners are occupied with the atoms, and also there is an atom in the middle, right? And this type of atomic arrangement we observe in chromium, tungsten, vanadium, and of course another one here you guys are familiar with is the FCC crystal structure. And in this case, the faces of the unit cell, right, has atoms besides the corners, and we call it face-centered cubic. And of course, this unit cell repeats in 3D, forming the overall crystal structure. Okay, another ball model of FCC. And FCC, what type of materials are FCC materials? So usually these are aluminum, copper. So it is important to at least nickel to get an idea. For example, aluminum is FCC. Okay, so because being FCC will determine a lot of things, such as the properties, such as deformations during manufacturing, etc. So it will directly affect a lot of things. Therefore, it is better to just get an idea. Let's say for aluminum it's FCC, copper it's FCC, nickel, silver, gold. Okay. Okay. And also FCC is most densely packed configuration. So that means atoms are packed in a way that leaving out less space in between them. So this is important again in determination of properties. And again, this is directly related to the bonding, atomic bonding itself. For example, the BCC structure, it is covalent bonding, and covalent bonding has some directionality to it, meaning atoms cannot approach to each other at all directions. Therefore, that is less packed compared to FCC and HCP. Okay. So therefore, let's see, the next one is HCP, hexagonal closed packed structure. Which materials have HCP configuration? Okay, beryllium, cadmium, cobalt, magnesium, zinc. Okay, so these are HCP crystal structures. So all these three arrangements, they will keep the same arrangement, and they can be modified by the addition of atoms. And what we call this alloying, right? For example, there will be spaces in between the atoms that are packed, let's say FCC structure or BCC, right? We are seeing that there are some empty regions, even if the atoms are packed very well. So these empty regions, we call them interstitial sites. Let's say the carbon atoms can be put into those interstitial sites within the iron, and this will form, of course this is alloying, this will form the steel, right? The iron together with the carbon, it's going to be called steel. Or when we say aluminum alloys, right? What do we mean? We have the aluminum, which is in FCC structure, and within those empty regions we are putting in different type of metals, but mainly it is aluminum, and the interstitial sites are incorporated with different metals and different elements, and this will give us what we call aluminum alloy, right? So that is the alloying. Of course, this is done to improve the properties. Okay, there is a reason we want to improve the properties. Therefore, we do alloying. Okay, adding elements, atoms to the structure of the metals, basically. Okay, so there is also another term here, what we call polymorphism or allotropism. What is that? It means many shapes. So that means there can be more than one type of crystal structure in metals. So for example, that metal is, for example, let's say iron, okay, can have a BCC, can also have FCC structure, depending on temperature, depending on composition. So when we say iron is, let's say, FCC, it doesn't mean it cannot be BCC, okay? Because there's alpha iron that is BCC and gamma iron that is FCC. So sometimes these materials where you can have more than one type of crystal structure like the iron, these are what we know as the allotropism or polymorphism, okay? And this is, of course, so important in manufacturing and processing of metals, because we know that the crystal structure will directly determine basically the properties. So allotropism is something very important in the heat treatment of metals, in the welding operations that we're gonna see. Okay, so I also would like to note that most metals that are used in manufacturing operations, that they are polycrystalline. Okay. All right. So here Another explanation here, the topic I covered previously, what is single crystal, what is a polycrystal. You see different grains, different regions, the atoms align different direction, right? That is what we call the polycrystal. And of course, what is amorphous? When we say amorphous, there is no certain arrangement of atoms, okay? And therefore, that is what we call amorphous. Of course, that will affect every type of property, such as the optical transparency, etc. And it will affect the strength, and optical, electrical properties, and every property basically will be affected by such random arrangement of atoms, not in order, right? Okay. So when a material is subjected to external force, it first undergoes elastic deformation. What we call elastic deformation is when we actually remove that force, it can go back to its original shape. But if you apply sufficient force and pass that elastic deformation region, basically the material undergoes a permanent deformation, or what we also call plastic deformation. At this point, even if you remove the force, now the material cannot go back to its original shape. And question is, how does actually the plastic deformation happens inside the material? By two ways. One is deformation by slip. The other is deformation by twinning. Slip is basically by the application of course, you apply tensile stresses, deforming the material, and the shear stresses generated due to these tensile stresses. And the shear is basically causing, right, the atomic planes to slip over each other. You are under the shear stress, like this in the image we are seeing, right? And therefore you see these slip planes here, where the slip is happening in the material. Okay, and these slip planes, of course, determined, we're gonna see, by the most densely packed plane inside the material, because those planes will require the least amount of stress to start the deformation. Therefore, it starts with inside most atomically packed planes, and these planes will be different for different type of crystal structures. So FCC, BCC, those all will be having different atomic planes, that where the shear starts actually. So think about this is sliding of playing cards against each other. So another way here is twinning, and this is least common. So the most common is slip, but certain materials well, I couldn't speak. Certain materials will experience, twinning, not all of them, okay? So as an example here, tin cry, you can watch the video, the link is given in Canvas, the tin, okay? So when the materials are deformed by twinning, they will make a certain noise, and it's like a crying noise basically. You can watch the YouTube video and see what that sounds like. So what is twinning actually? It involves the generation of a twin around the line of symmetry subjected to shear. Here you can see, guys. This is much rarer form of plastic deformation. A very important definition, anisotropy. It is very important, especially in manufacturing. It affects the formation of defects, or if it affects if the material is processed in a certain direction, what will be the ending properties will be like, right? So it will affect a lot of things. So what is anisotropy? It is basically a single crystal that exhibits different properties when tested in different directions. So that means, let's say we have a single crystal, right? Atoms are aligned in a certain direction. Therefore, when you test the material will show different properties in different direction. A lot of properties will be affected by this. Mechanical properties, magnetic properties, electrical properties. So at different directions, if the material is basically exhibiting different properties, then that is what we call anisotropy. So let's talk about slip systems. Slip systems is basically the combination of slip planes. So at certain planes the slip happens, right? And these planes will differ depending on your crystal structure. FCC, BCC, HCP will have different slip planes. Slip planes, and together with slip planes, the slip direction will be giving us the slip systems. So the slip or the deformation will happen at a certain planes, at a certain direction. And those directions and those planes are usually most densely packed atomic planes or atomic directions. This is because the slip first starts at those direction or those planes, because these directions or planes will require the least amount of stress to start the slip. That's why once you reach that critical stress on those certain planes and direction, the slip happens. And in this case, in this figure, we are shown how the slip planes will look like. Okay, so a single crystal, actually there are grain boundaries for each grain can be called as a single crystal, because within that single crystal or a single grain, basically the atoms are arranged in a certain order, right? And the slip will start on those most densely packed planes and directions. And as you can see, we are shown which planes this material is experiencing the deformation actually. Okay, so of course these will differ, as I said, depending on what crystal structure you have. Do you have BCC, FCC, or HCP? Okay, so for example, in BCC there are 48 possible slip systems, meaning the combination of planes and directions. So if you remember, I told you guys, BCC structure are usually a result of the presence of covalent bonding in the structure, because the bonding is directional and it will create less packing. And therefore BCC metals will generally have a good strength, okay, and a moderate ductility, and therefore will require high shear stress. FCC structure, on the other hand, has 12 slip systems, and FCC and HCP, those are most packed crystal structures. Therefore, slip is easier, meaning it will require lower shear stresses compared to BCC, and has a good ductility and have moderate strength, such as these metals, remember, aluminum, gold, copper, silver. And HCP crystal structures, they just have 3 slip system. Okay, so that creates a low probability of slip. And usually these metals can experience twinning, rather compared to slip, and such as zinc, like tincry, right? Zinc, magnesium, beryllium, and they are usually brittle at the room temperature because of the less probability of slip happening. Okay, so now the imperfections in crystals, like defects, point defects, linear defects, planar defects, and bulk defects. So defects, they are very important in the structure. In terms of manufacturing, they are usually the cause of manufacturing defects, and they help us to determine the manufacturing parameters, because linear defects such as dislocations, those are the main reasons that we can deform metals plastically permanently. And of course, how easily these dislocations will move will determine the stresses that needs to be applied during the manufacturing and shaping of the part. And of course, those directly related to the cost of the manufacturing processes. So let's start with looking at the point defects. And what are point defects? They can be impurities, right? So they can be vacancies. In the figure, we are seeing a vacancy. So basically, a missing atom or an interstitial atom, like the carbon inside iron crystal structure, or a foreign atom that is replacing the atom of the pure metal, like the one substitutional impurity. Okay, or the atom itself is getting into a interstitial side. It is the self-interstitial atom. So linear defects, those are dislocations in 2 types, edge and of course screw dislocations. And edge dislocation is like an extra plane of atoms in the structure. And screw dislocations, basically you can imagine as if you cut the crystal along a plane, it is like slipping of one half or across the other, right? So that is the screw dislocations. Those are line defects in the structure. And edge dislocations, they are extremely important, okay? And because they are the main reason where we can deform the metals. Actually, how people figure this out, because so initially, theoretically, they calculated how much stress will be required to deform a material. Of course, when they are doing theoretical calculations, what they did is assume when the material is deforming, you are breaking the bonds of the atoms to shape the material. So therefore, theoretically, very high strengths, very high stresses were required to shape, to deform the materials. But in practice, they didn't observe that this much stress will be required, just as calculated by the theoretical calculations. So they need to understand why this was happening, why less stresses are required compared to the theoretical calculations. So therefore, this dislocation theory was generated. So it was figured out that actually there is this line defect in the structure here, extra plane of atom, right? And that is the one that is only moving and breaking the bonds and then reforming the bonds inside the material, okay? And since only a single bond is breaking and also a new one is forming at the same time, of course, breaking and forming the bonds, one will require energy, one will generate energy. So this was actually requiring much less energy than what is calculated with the theory, right? So overall, just one extra plane of atoms, if they move along the structure by the shear stresses, you see an actually change shape, right? You see the overall the material changed shape. So we have millions of dislocations inside. Of course, this is just atomic scale change shape, but millions of dislocations move at the same time, causing a macroscopic structural change, deformation that we see inside, outside the material. We can see that, right? What is going on inside is actually the dislocations are moving. This is very important because then if you can understand that if deformation is happening by the dislocation motion, which you can watch in this YouTube link, which is also in your canvas, then you can figure out if you don't want the material to deform that easily, so you can say I should then prevent the dislocation motion somehow. If I can prevent that motion, then I will strengthen the material. So therefore people put extra atoms to prevent these dislocations impeding their motion, right? They can put extra atoms inside the crystal structure, imperfections, atomic imperfections they can put in, or they can do heat treatments, etc. In all cases, you can explain the behavior by understanding how this dislocation motion was affected. Okay, so therefore it's very important to understand that. So there is this work hardening and strain hardening, very important, because usually when we manufacture materials, we need to work on them, right? We need to change their shape. And when we actually changing their shape, actually we are making the material stronger. So that is called work hardening or strain hardening, meaning as you deform the material, you are actually making it more stronger. Okay. Each time you work on the material, it is gonna get stronger. So you need to apply more and more stresses to be able to continue changing its shape. Why this is happening? Why the material strength is increasing? One is when we deform the material, we are disturbing the crystal structure, making more defects inside, right? Making more dislocations, more line defects when we try to work on the material, disturbing the crystal structure. So since there will be increase in the dislocation amount, they will start to prevent their motion. They will affect each other's motion. So they will entangle. So the entangled dislocations. Plus, dislocation motion is also prevented by other defects inside the material, such as grain boundaries, impurities, inclusions. Okay, so overall the increase will happen when you work on the material in terms of its strength and the hardness. So its strength is increasing and its hardness is increasing as you keep working on the material, as you keep changing the shape of the material. So next we're gonna talk about grains and grain boundaries. So this is gonna be planar defects. Okay. So many times in manufacturing we start with the liquid molten metal, right? And then it solidifies. When it's solidifying, grains form in the structure. And of course the number and size of these grains will depend on the rate of nucleation. Okay, how fast your cooling, for example, will determine the number of nucleation sites. Of course, this will determine how many grains you have, etc. So in general, if you do rapid cooling, quickly cool the material, the molten metal, you will end up with small grains during your processing. And the small grains means higher strengths, because remember, if you are able to prevent the dislocation motion, you are strengthening the material. And smaller grains means more obstacles for dislocations. Okay? Because more surface area, more grain boundaries. And slow cooling, you provide the material more time while you cooling it, so there you have more time for diffusion, for atoms to move around, and therefore it will have larger grains. And larger grains means, of course, low strength and hardness. And of course, this will also cause, whenever a material has large grains, that will cause a rough surface appearance. And it is called orange peel. This is observed especially during the stretching of sheet metals. We see in the figure an illustration of the stages of solidification of molten metal, and each square here represents a unit cell. And of course, nucleation starts at random sites in the molten metal. And you can see that each of these have different orientation. And as solidification continues, at the end, you are able to see individual grains. You are able to see, right, individual grains and grain boundaries right there, right, the grain boundaries that are forming in the structure. Therefore, since now this is called a polycrystalline structure, and the polycrystalline structure, since it has grains in which the atoms are aligned in all directions, right, in random directions and on all directions in general, therefore the property, the behavior is going to be isotropic compared to a single crystal. Single crystals, because the atoms are aligned only in certain direction, depending on which direction the property will change. But isotropic means the properties will not vary with the direction in all directions. If you measure the strength, it will be the same. If you measure the conductivity, it will be the same. Or magnetic properties in all directions will be the same if we are talking about isotropic material. So we understood that basically grain size has a major effect on the mechanical properties of metals. Okay, so, and we said that if we have a large grain size, that is usually low strength and low hardness. Okay, and we can observe some rough surface appearance like orange peel during the manufacturing. Okay, you can actually observe it with your naked eye. So how in manufacturing people characterize and use or make use of these grain sizes? Okay, so there is this equation, Hall patch equation. This equation relates the yield strength of the metal to the grain size. So you can understand, depending on the grain size, what should be the yield strength. Okay, so here is that equation we see, and S is the engineering strength, right? And S with a subscript Y is the yield strength. And SYI is the yield stress for a large grained material. So compared to that, we are looking at actually how much with the grain size this yield strength is increased. So the K here is basically a constant, and D is the mean grain diameter. Okay, so how the grain size is measured? This is done under microscope. At a certain magnification, you take the image, okay, and then you count the number of grains, and then through an equation, in here we are seeing, we are calculating the American Society for Testing in Materials grain size number, okay, N, and this is used in the manufacturing. So usually the microscopic image is taken at 100x, and then that image, you work on that image, you select an area, basically per square inch. So you select that area and count the number of grains and put it in this formula, and this will give you the ASTM grain size number, okay, that is used to characterize the material during manufacturing. And let's say usually, for example, the grain size of 5 and 8 is considered fine grained, and a grade of size 7, for example, usually accepted for sheet metals for making automotive bodies and appliances and kitchen utensils, right? So in this table we are seeing the ASTM grain sizes, right? And grain sizes and corresponding number of grains per area, basically, or per volume. Okay, so you can actually see that for a grain size of 11, let's say, within an area you have this much grain. So it's a very, very tiny grains, very strong material, right? So I will solve an example about this particular topic, and you should guys watch that example in the canvas. Okay. As we have talked about, grain boundaries are very important, and grain boundaries influence the strength and ductility of metals, because we learned that dislocation motion is prevented by the grain boundaries. So another important thing is grain boundaries, because the atoms around the grain boundaries are more free, more disordered. They are not more orderly packed like the more inner regions of the material. In the grain boundaries, there's less packing, right? Atoms are more free. It makes them more reactive because they want to be able to be stable, react something. And therefore, usually if there's going to be a reaction such as corrosion, or if there's going to be an etching with the acid, those type of things will going to happen in the grain boundaries first. And this is important in manufacturing. If there's especially forging, there is hot forging and corrosion happening, and those type of manufacturing processes, the reactions will start at the grain boundaries. And grain boundaries also take important in terms of plastic deformation. The plastic deformation that is happening at elevated temperatures. What we call this actually creep. So what happens is the grain boundaries, like this one, let's say these are grain boundaries. This one is a grain boundary, right? And they will slide over each other. So the grain boundary sliding is actually a type of plastic deformation compared to slip and twinning, but this time this is a plastic deformation type that can happen at elevated temperatures. So another important thing, grain boundary embrittlement. In this, when exposed to a low melting point metal, a normally ductile and strong metal may crack. And what happens is these elements basically weaken the grain boundaries. So there are different types, liquid metal embrittlement, and in this case basically the embrittling element is in the liquid state. And if it happens at temperatures below the melting point of the embrittling element, then that is called solid metal embrittlement. Another one is hot shortness, that is caused by the local melting of basically an impurity along a grain boundary at a temperature below the melting point of the metal itself. This way it is weakening basically the grain boundary. And temper embrittlement is caused by the segregation, or other words, movement of these impurities to grain boundaries. Again basically weakening the grain boundaries. Okay. So when we have a polycrystalline metal, as you see, the grains are equixed. That means they have equal dimensions in all directions. If they subject to the plastic deformation at room temperature, that is what we call the cold working, right? So we are working on the metal at cold temperatures, meaning at room temperature. Those grains, you can see that they are deformed and elongated. after the deformation, such as under compression, like we do during the forging or the rolling processing, and the grains are actually becoming deformed and elongated. And we learned that such deformation makes the material more stronger, because what happened, we are disturbing the grain structure and the dislocations entangle to each other, increasing the strength of the material. So of course the strength increase will depend on how much strain the material is subjected to, how much you deform the material, because if you deform that higher, like the higher the deformation, the stronger the metal will become. Okay, and basically also you are here increasing the number of dislocations, right? And then this way strengthening the material due to the reasons we just described. So the grains are elongated in one direction, right, and contracted in the other direction. Therefore the material has become anisotropic, meaning in certain direction the properties are different than the other direction, right? So vertical direction property is different than the horizontal direction. So that's what it explains here. Of course, many parameters will affect this anisotropy. For example, the temperatures at which the deformation is taking place, or how uniformly the metal is deformed. For example, if you look at the illustration of a crack in a sheet metal, so this is the sheet metal, of course, that is subjected to bulging, right? And there's a crack formed during manufacturing. And this direction of the crack will tell you that the ductility of the rolled sheet metal is actually in transverse direction lower than its rolling direction. And therefore the crack will be observed in that direction. So now we have learned that with plastic deformation or cold work at room temperature, right, we are causing distortion of the grains, basically, and grain boundaries. And this is causing an anisotropic behavior, like we have seen in this example. And we also increase the strength, and of course increasing the strength means a decrease in ductility, right? And of course there is a way to reverse this. So and then that process is actually called annealing. So think about this way. So you are changing the shape of a material, right? You are doing cold work, and how much you can go keep changing and deforming the material, because every time you work on the material it gets stronger and stronger and stronger, and getting stronger means getting brittle or reduction in ductility, right? So you cannot keep working on the same material over and over again. So therefore in manufacturing, once you work on the material, you also need to reverse these effects if you want to continue keep shaping the material, because the material will become brittle. You cannot continue changing the shape. Therefore, we have a process called annealing, where basically it has 3 stages: recovery, recrystallization, and grain growth. So in this figure we are seeing that we have cold work grain structure here. Okay, and in the recovery stage, of course, what is happening here is, so this is below the recrystallization temperature. Stresses are relieved that are inside the material, okay, because deformation causes stress inside the material, and those stresses are decreasing as we increase the temperature during the annealing process. Okay, and at some temperature we will reach the recrystallization temperature, and the recrystallization temperature defined as the temperature at which complete recrystallization occurs within 1 hour. So what happens is new equexed shaped grains are forming from the previously cold worked grains, okay, as you can see here. This causes the strength to decrease and of course ductility to increase, okay, during this recrystallization period. And some metals, interestingly, like lead, tin, cadmium, zinc, okay, so their actually recrystallization temperature is at room temperature. That means no matter how much you cold work on them, because you also keep, even if you disturb the crystalline structure, they are also at their recrystallization temperature, right? So you cannot actually work hard on them. They won't get stronger as you deform them, okay, because it's like you are also doing annealing at the same time. After this recrystallization stage, of course, as you keep increase this temperature increase means you are increasing diffusion, atomic motion, therefore grains will start to grow. So you will start to have larger grains. Okay. Okay. So if we look at some terminology here, when we said cold working, we are talking about deforming the material at room temperature, and sometimes we need to do hot working, basically work on the material above the recrystallization temperature. So there are many parameters why we cold work or hot work. You need to understand that we need to make sure we are selecting the most economical manufacturing parameters, because remember, when you are deforming the materials, you need to apply stresses, right? And how much stress you're going to apply, of course, will determine the power of these instruments. And you don't want to increase the power, because this will economically affect the price of the manufacturing, right? So people need to come up with ideal optimum manufacturing parameters that will give them the most economical manufacturing conditions, basically. So sometimes they do cold working, and the cold working will give you an increased strength for the material, and there are some cases where we need to do hot working, and again this is above the recrystallization temperature. If you choose a temperature in between, it is going to be called warm working. And the temperature ranges are given here. Okay, so T is the temperature of your manufacturing process. Tm is the melting point of that metal. So this, depending on this ratio, it is called cold working, warm working, or hot working. basically. Okay, with this, here is a summary. We have learned crystal structures. We have learned within these structures we have defects and imperfections, and those are very important. And we learned about grains, and we learned that there are different ways the plastic deformation can take place, but it is mainly with slip. And we have learned that when we work on the material, change its shape at room temperature, its strength and hardness increased, its ductility is decreased. And we have learned the grain size has a significant effect. When it's reduced, the strength is increasing. And grain boundaries can also be responsible for creep, the form of plastic deformation at elevated temperatures. And the metals, depending on manufacturing parameters that are selected, can be deformed at room, warm or higher temperatures. And of course, deformation temperatures will affect overall properties of the metals, right? If you work on cold temperatures, cold working, it will increase the strength, for example. Okay, so after each chapter, you guys have to do the homework in the syllabus, and you just have to listen to the lecture and take the test on Canvas. There is no time limit, and I think you can just save, get out and get in as many times as you want, and just make sure you submit. Okay, press the submit button, and there is a deadline. You guys need to check the deadline in Canvas. And that's it for the first chapter, and then next we're gonna see mechanical properties. We're gonna review them. Okay.